Hello everyone, good to see you again. I call myself Mr. U.S. Patil, working as assistant professor at Sharad Institute of Technology, College of Engineering, Adrao Ichalkanji, which is at Kolhapur district, Maharashtra. Today we are going to see adaptive control systems in CAD. So let's get started with an introduction. The adaptive control machining has been developed to optimize machining characteristics. The adaptive control, if you see that adaptive control AC, machining is an evolutionary outgrowth of numerical control. It is a control system that measures certain output processes variables and uses these to control speed and or feed. Some of the process variables that have been used in adaptive control machining systems includes spindle direction or force, torque, cutting temperature, vibration amplitude, metal removal rate, cost per volume of the metal removed, and horsepower, etc. The adaptive control system is a logical extension of the CNC mechanism. And the CNC mechanism, the cutting speed and feed rates are prescribed by the part programming as we just discussed. The determination of these operations parameters depends on the knowledge and experience of the programmer regarding the workpiece, tool materials, coolant conditions, and other factors as well. By contrast, in adaptive control machining, there is an improvement in the procedure rate and reduction in the mechanism or machining cost as a result of calculating and setting of the optimal parameters during the machining. If you see the origin of this adaptive control mechanism system is originated out of research in early 1970s sponsored by US Air Force, and the initial adaptive control systems were based on analog devices representing the technology of that at that time. The today adaptive control was microprocessor based controls and is typically integrated with an existing CNC systems. The what definition of this AC machining? Uh, the For the machining operation of the term AC denotes the control system that measures certain output variables and uses to control speed or feed. Some of the process variables that have been used AC machining system include spindle direction, force, torque, cutting temperature, and horsepower, as we just saw. If you see here, the adaptive control feedback provides sensors uh, information on the machining process variables such as spindle direction, force, torque, cutting speed, cutting temperature, workpiece tool, air gaps, material property, variation, vibration amplitude, metal removal rate, cost per unit volume of metal removed, and the horsepower. The data processed by the adaptive control that converts the process information into the feedback data to the incorporate in the machine control unit. So this is what a adaptive control machining system, that a CNC system is here, so drive commands are here, again position feedback something is here, if there, so it would be here, the machine tools are here, processing machining processes are carried out with the help of sensors. Again it gives a feedback to adaptive control, it customize a strategy and performance index over here, so again it forward to CNC system to operate. Yes. So here the adaptive control is basically a feedback system that treats the CNC as the internal unit and in which machining variables automatically adapt themselves to actual conditions of the machining process. If you see IP, that is performance index, is usually an economic function such as maximum production rate or minimum machining cost. If you see the function of AC, there are three functions of adaptive controls are the identification function, a decision function, and modification function. The main idea of AC is the improvement of the cutting process by automatic on line determination of speed or cutting or feed, you say. The AC is basically a feedback system in which cutting speed and feed automatically adapt themselves to the actual condition of the process and are varied according to the changes in the work condition as work progresses. So where definitions of functions, identifications of functions are, this involves determining the current performance of the processor or system, and the indication of function is concentrated with determining the current value of this performance measures by making use of the feedback data from the processes, isn't it? If you see decision of function, once the system performance is determined, the next function is to be decide how to control the mechanism should be adjusted to improve the process performance, isn't it? Then the decision procedure is carried out by means of a pre-programmed logic provided by the designer only. So where to use the adaptive controls? If you see, the main advantage of NCSCNC is that to reduce the non-productive time in a machining operation. This time saving is achieved by reducing workpiece handling time, setup of the job, tool changes, and other sources of operator and machining delay or machine delay. If these non-productive elements are reduced relative to total production time, large proportions of the time can be spent in actually machining the workpiece. Although NC or CNC has significant effect on the reduction of the non-productive time, it can do relatively little to decrease the in-process time as compared to the conventional machining tool. Here, the NC or CNC controls are sequences of tool positions or continuous tool path of the tool during machining. There is a very possible of spindle directions of increasing the cutting's temperature or work with tool air gaps or material property variations or machine tool vibration. These processes parameters waste productive time. The most promising means of reducing the productive time is the use of adaptive control. The adaptive control determines the process or proper speed of feed during machining as functions of variation in process variables such as work material hardness, width or depth of the cut, air gap in the part geometry, and so on. Adaptive control has the capability to respond to and compensate for these variation during the processes. And this is what we are saying here, adaptive control is not suitable for every machining situations. In general, the following characters can be used identifying situations where the adaptive control can be beneficially applied. That is, the in process time consumes a significant portion of the machining cycle, that is a portion of the total production time, right? And there are the significant source of variability in the job for uh, which AC can compensate. In essence, AC adapter speeds or feed to these variable conditions. The cost of operating the machine tool is high, and the typical job involves steels, titanium, and high strength alloys. The modification function, the third AC function is to implement the decision. While the decision function is logic function, the modification is concerned with the physical or mechanical change in the system, and the modification involves changing changing the system parameters or variables so as to drive the process towards a more optional state or optimal state. If you see classification of adaptive control system, there are two types, or you can say they classified into two types. So mainly here is three. This is what a geometrical adaptive control is, kind of a different parameter. We are considering here types, but basically there are two types. That is adaptive control with constraints, or you can say adaptive control constraints, and adaptive control optimization. And this is one geometric adaptive control. If you see ACC, that is adaptive control constraints, the object of here ACC are systems in which machining conditions such as spindle speed or feed rate are maximized within the prescribed limits of machines and tools constraints such as maximum torque or force or horsepower. The objective of the adaptive control is to manipulate speed or feed to maintain the major variables at or below their constraint limit values. The constraint defines the permissible range of operations. The constraint violation detection logic determines whether a process variable exceeded the predefined limit or not. If constraint variation has occurred, the ACU logic subsystem increments or de- decrements the value of the ACU output such that the process variable is within the predefined limit. The AC system, the correct feed and speed are automatically found, and it is not necessary to spend efforts on calculations of optimum feeds and speeds. The ACC systems do not utilize a performance index and are based on the maximizing machining variables. For example, feed rate, that is feed rate, subject to process and machining constraint, that is allowable cutting force on the tool or maximum power of the machine. And the objective of the most ACC type of the system is to increase the MRR during rough cutting operations. The basic structure of this ACC, the adaptive control are routine here, the spindle speed, feed limit, and required force. if you giving the adaptive control routine, it from here the feed rate and routine of clock of a timer, right? So it goes to x-axis and it again longitudinal of z-axis control the loop from its position and velocity sensors of these four sensors, all those things it gives here. Again it comes for AMP and ADC to give adaptive control routine, hence it goes to perform here, right? So this is basic structure of ACC. Here if you see the ACC example, for example, to maximize the machining feed rate while maintaining a constant load on the cutter despite variations in width and depth of the cut. In a normal CNC systems, the feed rate is programmed to accommodate the largest width and depth at a particular cut, and this small feed rate is maintained along the entire cut. As the result, the machining rate is reduced, isn't it? By the constant, by contrast with the ACC system, the maximum allowable load, that is cutting force on the cutter, is programmed. As a result, when the width or depth of the cut are small, the feed rate is high. When either the width or the depth of the cut are increased, the feed rate is automatically reduced and consequently the allowable load on this cutter is not exceeded. The result is the average feed with ACC is much larger than its programmed counterpart. The ACO, that is adaptive control optimization. The adaptive control optimization optimizes the overall efficiency of the production process or selected process parameter. In this form of adaptive control, a figure or merit or M is specified of for the system. The figure of a merit is called merit function, which is a numerical measure of efficiency. The magnitude of a figure of merit indicates the merit or desirability of the given combination of process variables. The figure merit is the production rate or cost per volume of the metal removed. The objective of the adaptive control is to optimize the figure of merit by manipulating speed of feed in the operation. The ACO system for NC machining tool is control system that optimizing performance of index subjects to various constraints. It is basically sophisticated closed loop control system which automatically works in the optimum conditions, even in the presence of workpiece and tool material variations. The basic structures of ACO system, this is what. Here if you see here, program dimensional data, feed rate or speed rate, numerical control systems here, the optimized computer and performance computer. From here the tool wear rate, a metal removal rate you can get from data reduction subsystem. So here if you get the torque, temperature, vibration from the sensors and machine tool while numerical control system is operating, this is position and speed commands. And if you're going for a feedback, a portion of feedback, this is what going a feedback. Here from again a feed correction is here. Yeah. This is what the basic structure of ACO system. If you, what is the drawback of ACO, adaptive control optimization? The main problem is that this requires online measurement of tool wear. So far there have been no industrial stable methods developed for the direct measurement of tool wear. Indirect measurement assumes that the tool wear is proportional to other measurable variables such as cutting forces and temperatures. The drawback of using these indirect measurements is that the variation in their values can be caused by process variations other than tool wear, such as workpiece hardness or cutting coordinates. Sorry, cutting conditions. Thus, making it difficult to identify the tool wear effect from the effect of the other parameter variation on the measurements. If you see last one, that is geometrical adaptive control, that is GAC, are typically used in finishing machining operations. In GACs, the part quality is maintained in real time by compensating for the deflection and wear of cutting tools. The objective of CA is to achieve the required dimensional accuracy and a consistency of surface finish of machined parts despite tool wear or tool deflection. The drawback of GAC, both the dimensional accuracy and the surface finish are affected by the flank wear and the crater wear of the tools, which deteriorated which is deteriorated during cutting. These variables cannot be measured in the real time. Neither can they be accurately predicted from offline tool testing. The benefits of AC is the increased production rate. That is very important. The increased tool life as well, greater part protection, and less operator intervention. The limitations, the major drawback is the unavailability of suitable sensors that have a reliable operations in a manufacturing environment, that is tool wear sensors. And another problem is the interface of AC system with CNC units, as yet manufacturers have not standardized interfaces. So thank you so much for this is what we have gone through uh, adaptive control machining systems. So next we'll see in a next another topic soon. Thank you one and all.